Hello, and welcome to the second video in this series of graphs in thermodynamics. Today, we'll be covering PV phase diagrams. In this video, as we're looking at PV phase diagrams, we will have pressure on the y-axis, where pressure is the force exerted per unit area on a substance, and specific volume on the x-axis. Before we dive into how an isotherm is formed, I wanted to briefly explain why the lines are curved on this graph opposed to straight lines on a typical TV graph. Now they're curved as assuming our substance is an ideal gas, that is, that it follows PV equals nRT. We also know that it follows a similar equation, PV equals mRT, where R is the specific gas constant opposed to the universal gas constant. Through some algebraic manipulation, we can see that P is equal to RT over V, and as R and T are constants, this is because we're assuming it's isothermal, pressure is inversely proportional to specific volume, hence the curved nature of the graph. So, let's go through how an isotherm is formed. Let's imagine we have a fixed mass of a superheated vapor in a closed system, like a piston. A force is gradually applied to the gas, increasing pressure. At higher pressures, the density of the vapor increases, and so specific volume decreases. When the intermolecular forces become strong enough to overcome the kinetic energy of the gas particles, the molecules condense into a liquid phase. This is because the system seeks to maintain equilibrium under the new pressure, and the liquid phase becomes more thermodynamically stable. This means that as pressure is increased, the boiling point decreases. So, if we now look at the formation of our isotherm, we notice that as pressure applied to the superheated vapor is increased, the specific volume is decreased until it reaches its saturation pressure. At this point, as mentioned before, the intermolecular forces are at dynamic equilibrium with the kinetic energy of the gas particles. So above this point, the intermolecular forces overcome the kinetic energy of the gas particles, resulting in the formation of bonds and ultimately condensation. As the substance transitions from a saturated vapor to a liquid vapor mix, the particles' proximity is decreasing, hence the decreasing specific volume at constant saturation pressure. After the phase change is complete, the substance is in a single liquid phase region, whereby increased pressure still decreases the specific volume, resulting in this final curve. This diagram shows the different PV curves for different temperature isotherms. I will now try to explain the reasons for the differences between these curves. Firstly, you may notice that the saturation pressure is higher for the higher temperature isotherm. This is because at higher temperatures, the molecules within the vapor have higher kinetic energies. This means that a higher pressure will need to be exerted in order for the intermolecular forces to overcome the kinetic energy of the molecules, and therefore condense. You might also notice that the specific volume at the saturated vapor point is less in higher temperature isotherms. As mentioned previously, this is because at higher temperatures, the saturation pressure is also higher, meaning the vapor is denser as it is subject to a more compressive force, resulting in a lower specific volume. However, the specific volume at the saturated liquid point is greater in the higher temperature isotherms, because when the temperature of a liquid is increased, the kinetic energy of the molecules rise, pushing each molecule slightly further apart, increasing specific volume. This means that again, the saturated liquid vapor region shortens as temperatures are increased up to the critical point where the saturated liquid and vapor are in thermal equilibrium. Thank you for watching, and I hope you enjoy our next video on the vapor compression refrigeration cycle.